Okay, we'll try to keep this short. I know there's some reactions that we had up on the board. We just didn't quite get to those. Okay, so besides the bonding, what between an alkane and an alkene, what might be some different properties? You could say something about isomers. What else would there be? Even that up there, when it comes to derivatives, if they're pointing, the hydrogens are pointing in opposite or same directions, we refer to those as cis or trans compounds. But which one has more isomers, the alkanes or the alkenes? Alkanes? Are you sure? It's not the alkanes. So yes, it is the alkenes by default, you could say. Okay. Did you maybe work at the meet yesterday and think, gosh, I remember those days, I miss them? Nope, not at all. Okay, fair enough. All right. So when we, as we move on, we're going to start talking about these addition reactions. Now this was correct. This is where we left off with, right? It might have been this one instead. But I thought it was this one. Okay, we did that one. So we begin with what we call addition reactions. Okay. So we're just a little behind. Not too bad. We just didn't get to the reactions we wanted to see. So, we've been talking about this point right here, okay? Alkenes are highly reactive, alkanes are not. And it refers to the saturation. So, which one of these two is the saturated type? Alkenes or alkanes? Which one of them is saturated? Are we sure? Yes, you are correct. It is the alkanes that are saturated, okay? So when you described those reaction mechanisms, sometimes the result was no reaction. Why was that? So when you were doing those reaction mechanisms, sometimes the answer was no reaction. Why is that? Yes, you needed to have a catalyst because the alkanes, as you already established, are saturated and are highly stable. Unlike that of the alkenes, which are highly reactive and unstable. Band students are coming back in. They say, is it sprinkling out there? No, it's not. Could be. I was thinking about this morning. I wonder if farmers may start combining corn before they get the beans done. I don't know which one dries quicker, but I feel bad for the farmers because it's just the idea of having to maybe pay for the drying of those crops, which takes away from, of course, the bottom line. Okay. We're obviously, well, we don't have class tomorrow, so with that, we're not going to get to. I'm just not going to give you an assignment over the weekend just to say that, oh, we're going to keep on schedule. I don't really believe in that. But I want to finish this and then finish these addition reactions, and then that'll be it for today. Then I want to go over what we had on the boards yesterday, and then the rest of the time will then be yours. Because it'll take us a little bit of time to get through those reactions. Because I think that's a good place. Yeah, because we'll get to reduction reactions. Okay, so the examples that we had up on the board yesterday were as follows. So I distinctly remember, I think we had, what was it, two pentene? Does that sound right? Plus hydrogen, I think. Okay. And some aluminum there. And the next one down, I want to say was it propene? Maybe? Okay. And hydrogen. Okay. Okay. And then the last one was just propene, correct? Or pentene. Okay. I do believe that's fairly accurate for where we left off. Okay. Now, so how would we draw to pentene? Okay, remember when we reverse engineer this, this is our family, this is your parent chain, and then that 2 is significant for another reason. Okay, so we want to start with our parent chain, which is how many? Okay, so this is telling you somewhere within those 5 carbons there's something significant. Okay, so then where's that at then? Okay, so since there's nothing after this 2, it doesn't say 2-methyl, 2-ethyl, 2-chloral, or anything to that respect. If it's not naming a derivative, well then that's where the bond goes then. Okay, so after the second carbon, okay, there's our double bond. Then we'll go ahead and put our hydrogens in here. Now, if you are not paying attention, you can put them in too fast and put too many bonds on those carbons. Remember, it can only have 4. So now we've got our 2-pentene. Okay. So now when we react this with hydrogen, okay, how would we go about writing that when we say hydrogen? It's H2 because gases are, again, what? So rather than writing H2, we'll just write it like this, okay? So now, with our reaction, is this going to react? Yes or no? Yes, it will, because underneath that arrow it shows that we have a catalyst. We've got a metal reagent for this to take place. And the reason that that's significant, if you remember, we said that these alkenes are highly unstable, okay? Unlike the alkanes, which are highly stable, okay? Unstable and stable. But this one, okay, this double bond, or reacting with hydrogen, is an exception to the rule. And we have been, I want to say, introduced to that before. Remember when we said if you had T-butyl as a derivative and a methyl group, alphabetically, which one comes first? T-butyl does. We don't go by the T, we go by the B in butyl. The exception to those prefixes is when we have isopropyl or isobutyl, okay? That's an exception to the rule. This is also an exception. If we're going to get this pentene, this 2-pentene, to react with this hydrogen, we have to have a catalyst, okay? Because we said that these are highly, highly unstable. They're very easy to react with. Well, that's true with the exception of hydrogen. So then, when this reaction proceeds, which it will, because we have our metal catalyst, all of these bonds are now in here. That double bond is broken, okay? So all of these hydrogens are on there. So this double bond has now been broken, this one right here, okay? So how do we fill those two bonds in then for those two carbons? Where do they come from? What are we reacting that with? So we need to fill two in here, and we've got two hydrogens, so one would go here. You don't have to put the hydrogens in there. Remember, if they're just dashes, that means the hydrogen. But we want to color code these so we can see where and why that's coming from. Okay. So now, if we proceed forward, how do we draw out propene now? What's the structure for propene? Again, if we reverse this, family, parent chain. 3 carbons. Okay? And then if you want to go top and bottom, that's fine, or top and the side, it doesn't make any difference. Okay? So some mistakes that can be made, and it's very easy to do that, is put another bond in here because we're so used to dealing with the alkanes. Again, it's just easy to do. It's just one of the aspects with practice. Hopefully that goes away. Okay? So now we want to react that with some hydrogen. So H and H, or H2. And what do we get for a product? That's a low down dirty trick on my part. That's correct. This does not react, okay? Because the difference that what we see is when this reaction proceeds, this has a metal catalyst. This one does not. It's missing here. So then as we try to go forward, we do not get a reaction. Okay, so as we proceed with pentene now. The only difference between these two is where the double bond is. So since there's nothing here, if you really wanted to be specific, you could say 1-pentene. So we will put these in here as such. Okay. So I'm going to color code this again. So plus chlorine, chlorine. Now remember, we had said that hydrogen is an exception to the rule. And we've got an alkene and we've got a halogen. You've got a 50-50 chance. Is that going to react? Remember, we said hydrogen was an exception. The exception that what we meant is this has to have a catalyst, even though this is highly, highly unstable. This is still highly unstable, but this is no longer halogen anymore, so this reaction does proceed, okay? Even though it does not have a catalyst. So we do the same thing. We're going to draw out all 5 carbons. You can safely put all of these in here. And then what would go on our first and second carbons then? 2 chlorines. Okay. Okay. So we started with pentene, we reacted that with a halogen. So what was our final product then? How would we name that on the right? Yes. Yep, that is correct. Plus the comma. Yeah. Yep. 1, 2 dichloro-pentane. Now, I went through that really, really quick. Left side, are we on the bus? Middle, are we on the bus? And right side. The big things I want you to recognize here, okay? First of all, yes, we're dealing with the double bond. We want to see what we're reacting that with, okay? If it's hydrogen, it has to have a catalyst. If it's anything other than hydrogen, like a halogen derivative here, we do not have to have a catalyst, okay? So if there's nothing under that arrow, this reaction cannot proceed, okay? These alkenes have to have a catalyst when it comes to hydrogen. The only difference that I'm going to write up here, and we will discuss that on Monday when you come back, okay? That's where we will start. Oh, I'm sorry, can I erase this? Okay. With that is when it comes to our reagents, okay? And what I mean by that is this. If something has symmetry, we as humans, we have bilateral symmetry. What does that mean? If you have a mid-sagittal plane, where's your sagittal suture at? In the cranium. I know it's there, but where's it at? Yeah, it's right down the middle, okay? So if we have a mid-sagittal plane, that means we have equal left, for you, left and right sides, left and right sides, okay? That means there we have symmetry. So with this, if we have this, any one of the halogens, okay, what do we notice here? How did we write these reactants when we did them in our prior examples? We didn't write H2, we wrote it as H, H-H, okay? arrow H dash H. How do we do chlorine? Same thing. Okay, so we have a molecule here. Well, these are all molecules. These are diatomic, but here we change that to, of course, H-Cl. So we see a symmetrical reagent. We see the symmetrical reagent, the symmetrical reagent. What would you expect this one to be? Symmetrical or asymmetrical? What does it mean to be asymmetrical? They're not the same on both sides. This is symmetrical. This is symmetrical because it's the same on both sides. This is asymmetrical. What would you guess water is, symmetrical or asymmetrical? Because when you did in organic chemistry and balancing those combustion reactions, possibly, if you wanted to, how could you break this molecule apart? Write it as HOH, okay? Now, do you think, because that's got to be broken apart, so do you, now it's a trick question. This is not the, see, you got to be careful with how you say it. This is not asymmetrical reagent. See, it's not the whole word asymmetrical. It's not a space symmetrical reagent. That's why I always got to think about how I say that. This is the asymmetrical because we all know that hydroxide, this here, has a -1 charge. Hydrogen's got a +1. So when we write that, that's how it breaks apart. So that's why we consider that the asymmetrical reagent, because it breaks apart with a hydrogen on one side and a hydroxide on the other. This concept right here is going to be a reoccurring theme from here on out. When we talk about reactions, it's all about the water, okay? Because this, on how this reacts with different compounds. So just keep that in mind. Diatomic molecules, those are all symmetrical types. These bottom ones, these are all asymmetrical types. And that will become more important when we get into more reaction mechanisms next week, because if you're looking at your, your vocab sheet, one of your terms should be a rule named after a Russian chemist. Starts with letter M. It's Markovnikov. It's called Markovnikov's rule. Okay? And what that means is when it comes to these asymmetrical reagents, you have to denote both products. Okay? And what that means is, if you remember, if we had this from last chapter, just keep it simple. Okay, or Cl and Cl. So as a quick review, can we proceed? No, we cannot. Why not? There's no catalyst here. So we'll say there's a little bit of heat here now. Okay? So notice we could write this as Cl-Cl, okay? Just like what we did up here. Now, how many products do we get on the right side? 1 or 2? There's actually 2. This is one of them. Well, I'll put plus. What's the difference between those two propane molecules? Where do we want to put this chlorine? On the first one's fine. Then on the second one, okay? I can't remember the percentages. It had said on average this happens like 39%. This one's like 45%. So then 14, that leaves about 15%. I can't remember what, maybe just different impurities are left over to make up that difference between that to 100%. But the difference, the main thing that we're going to want you to know is that next week when we get into those, this is going to be known as the major product. This one will be known as the minor product. You didn't have to establish that last chapter because these two percentages were too close. When you get into reaction with the alkenes, this is about 85 plus percent, and it might even be closer to 90, and this is maybe 5%, and the rest is just impurities. Then you have to know or be able to label which one is the major, which one is the minor product. And the reason that's so important is because that would possibly be one of the reaction mechanisms that makes us or allows us to create isopropyl alcohol, which is probably one of the most widely used disinfectants. I don't want to say solvents, but it can be used as a solvent, because every time you go get a flu shot or anything to that nature, they take the swab of isopropyl, and then now pharmacists can give the flu shot, right? They're going to let you take the chance to okay, we'll pick up with this tomorrow or next week.